Good morning. Good morning, everyone. My name is Peng Zhiling, the Executive Chair of Local Organization Committee. I will serve as the master of this morning's opening ceremony. Before I introduce
Recording in progress.
Before I introduce today's speaker for the opening ceremony, I would like to give a very brief introduction of the background of this symposium. The first symposium was held in 2019, before COVID-19, with the name of International Workshop of Water Disaster Mitigation and Water Environment Regulation. The workshop was meant to invite top scientists in this field from all over the world to come together and discuss advances of research outcomes. The delegates were by invitation only at that time, and the total number was only 40 2 years ago. This year, we discussed the possibility of continuing this effort even under the influence of pandemics. We also wanted to make this symposium to be on regular basis in the future, say once every 2 years, and hosted by different research institutes all around the world. To report to you, this time we have more than 300 delegates, and some of them are actually unregistered and not paying for us. But I don't blame you, because this is because of limitation we have set for the maximum number of 300 delegates. In the meantime, we plan to form a new working group in International Association of Hydro Environment Engineering and Research with the name of Water Disaster, which hopefully will become a formal technical committee after a few years. So for this purpose, I would like to invite you to join us for the future works. And if any of you who want to host the third workshop after 2 years, please approach us and let us know. Now, without further ado, I would like to invite Professor Xu Weiling to make the welcome speech. Professor Xu is the local organization committee chair of this symposium. He's also the deputy president of Sichuan University, as well as the director of the State Key Laboratory of Hydraulics and Mountain River Engineering. Professor Xu, please.
Distinguished guests, ladies and gentlemen, today we are gathering here in Chengdu, the beautiful land of abundance, for the second International Symposium of Water Disaster Mitigation and Water Environment Regulation. As the chair of the conference and also on behalf of Sichuan University, I'd like to extend our warmest welcome to over 300 distinguished guests from 11 countries, and express my deep appreciation to all colleagues and brother institutes for the support to this event. This conference is organized by the State Key Laboratory of Hydraulics and Mountain River Engineering of Sichuan University, and the support of Journal of Hydrodynamics and the sponsorship of IAHR and IAHR China chapter. We aim to host a high-level and high-standard academic conference, not just for this year, but as a long-term regular event in the future. Sichuan University is among the key universities in China's national plan for the construction of world-class universities, and is the leading research university in Western China. The State K Laboratory of Hydraulics and Mountain River Engineering was founded in 1988. It was the earliest state K laboratory in China that focuses on the inland water conservancy and hydropower development. The laboratory had been long engaged in fundamental research in high dam engineering, mountain river dynamics, environmental hydraulics, rock mechanics, and hydroinformatics. It also plays a critical role in the mountain river protection, hydraulic project safety, and optimal management of inland water resources. The second International Symposium of Water Disaster Mitigation and Water Environment Regulation is a magnificent academic gathering in the field of water science and engineering. It will provide a platform for international academic exchange and collaboration in these post-pandemic days. The conference takes its theme as prevention and control of water disaster and construction of green ecological catchment. In the next 3 days, 134 senior and young scholars from 11 countries are going to share their scientific views in 4 technical topics, including water crisis and disaster mitigation, water pollution prevention and control, water ecological conservation and restoration, and frontiers in water science and engineering. By hosting this conference, we would like to contribute to the improvement of collaboration among universities, research institutes, and governments on water disaster prevention and water environment regulation. We also hope these events co-promote the development of relevant research activities across the world, as well as the strengthening of the water sciences and engineering disciplines in our university. Let's work together to achieve our goals. At the end, I'd like to express my heartfelt thanks again to all colleagues, guests, and friends for your great and consistent support to Sichuan University. I wish the conference a complete success and all of our distinguished guests and your families good health, pleasant work, and all the best. Thank you.
Thank you, Professor Xu. Now, can we connect to our next speaker? Is Professor Joseph Lee. He's going to make a congratulation speech to this symposium in the capacity of the president of IAHR. Professor Lee is a top scientist in environmental hydraulics. He used to serve as the vice president of Hong Kong University, vice president of Hong Kong University of Science and Technology. And starting from this year, he's moving to Macau University of Science and Technology and serve as a president. Now, Professor Lee, please.
Thank you, Chairman. Professor Xu, distinguished guests, ladies and gentlemen. On behalf of IHR, I would like to extend my congratulations to the opening of the second International Symposium of Water Disaster Mitigation and Water Environment Regulation. For those of you who may be new to IHR, I'd like to just start by saying a few words about the organization. IHR is a global organization. In its 86 years of history, IHR has made many contributions to the development of water engineering and the protection of the environment. We are a community of scholars and experts that produce high-quality knowledge products that lead the industry. Our IHR monographs, journals, and symposia have been defining the frontiers of research and practice in environmental fluid mechanics, hydraulic structures, and water quality control and adaptation to climate change. Many of our institute members have provided the scientific and engineering know-how to support sustainable development of many countries. So in short, IHR is a treasured international name brand. Over the past 2 years, IHR has been implementing a new strategic plan that revolves around several pillars. Inspire, disseminate, and categorize state-of-the-art knowledge, address global challenges, and promote diversity and enhance international collaboration. The strategic plan is underpinned by development along 3 directions: eco-hydraulics, AI and water, and engagement with Africa. Climate change, population growth, and urbanization give rise to many global water security issues. And the 4th industrial revolution also brings many opportunities for developing smart solutions for water resilience. And nature-based solutions to these challenges will offer a continuing stimulus to exciting developments at the interface of ecology, fluid mechanics, hydrology, and system science. And I hope IHR, our technical committees, provide a very good platform for different colleagues to develop the profession. Over the past 18 months, the coronavirus pandemic in 2020 has turned the world upside down. IHR has showcased remarkable resilience amidst the COVID crisis, delivering high-quality events that move the organization forward. Many of you would know that the first IHR online forum is undergoing very successfully this week. A series of virtual events aimed at bringing together the IHR community in the lead up to the IHR Congress to be held next year in Granada, Spain. The forum features 27 technical sessions and 16 IHR technical committees offering insights into current issues and solutions. So we welcome colleagues to support this event as well. Now back to this symposium. Climate change leads to extremes in hydrometeorological events, mean sea level rise, extreme rainfall, and temperatures. This can lead to disasters, floods and droughts, typhoons of unprecedented magnitude, changes in lake stratification that lead to increasing harmful algal blooms, etc. I believe this conference in Sichuan can be a good and important complement to the IHR online forum. And we are very, very pleased to be sponsoring this event. This second symposium follows the success of the first event 2 years ago, which I had the fortune of participating. And as a result of the encouraging responses from the community, many scholars have been discussing, as suggested by the chairman, the possibility of a new working group on water disasters and using this symposium as a featured event of this group. I very much appreciate the efforts, this initiative on promotion of international collaboration on this important issue, and look forward to the proposal and the new blood and new ideas injected into IHR. Finally, I would like to congratulate Professor Xu Weiling, the director of the State Key Lab, of Hydraulics and Mountain River Engineering of Sichuan University on the successful hosting of this conference. The State Key Lab has an excellent reputation for its promotion of engineering and research advances in high dam project solutions and the use of water resources in mountain areas. The lab has also successfully hosted the 35th IHR World Congress in 2013 and the 14th IHR International Symposium on River Sedimentation in 2019. In these post-pandemic days, I truly believe this event, this second symposium of water disaster mitigation and water environment regulation will provide a golden opportunity for our communities to reestablish academic exchange and collaboration and help us better face the challenges in the new era. So I wish the conference every success. I wish you all a very good event ahead. Thank you very much. So I turn over to you, Chairman.
Thank you, Professor Lee. Thank you, Professor Lee. And now I would like to invite all of you to step down on the first floor and to take a photo. Then after that, we will come back to this room for the keynote speech.
有没有那个5000的？
喂喂喂，
喂，我想想，
就是这儿还有个发言席嘛，你的意思？
我想想，我要问一下，
啊对，你忘了跟我那个，但是这分会场都准备了发言席，好像没了，就把分会场的先拿来用。
不是那个，喂，一会儿大会的话，你那是主持是坐哪个位置啊？要不要摆主持人席？不用摆主持人席吗？他肯定不能坐雷佳明旁边，他看不了报告的。要不要专门打一个主持人席？嗯。桌子转，不是，关键是桌子，我就问他要不要专门搭一个桌子这儿，还是你那是就在这儿？
林老师现在就在这儿，然后把这个桌子稍微转。
要么就给他摆个话筒在这儿，要么你在这儿。
就该放在，放在那边。
如果他需要的话，就随他说。要么你让他随他对了，让我看一下他可以不可以能。这个看他们小花
现在吗？对。
直接把这个，就叫我把凳子背着个，对，到时候相机在这儿，对，可以到大堂好吧？ 能达到是吧？拿到就行。
老师，会长期签个字，可以确定用作会议室签个章。这个价格可是经理给你们的协议价格，你们签字只是确认用过就可以了。
Oh, good morning. And great to see you online, Gretchen. It's been a few years.
Lovely to see you too. Hi.
So I see you're working out of China these days.
Yeah, I've been here for more than 5 years.
Wow, doesn't time fly since we were in Chengdu together?
Right, exactly. Chengdu has been my hometown, my second hometown for very many years, and I actually moved here, and I'm supporting the work of the Key Lab and the university in building this whole area.
不好意思啊，因为早没有按过来，早我就有这个对的。
是吧？是南方人还是北方人？来，浙江人。你应该还是比较习惯这种天气的。然后武汉也挺冷的。其实，白天跟晚上差不多。其实没有温差是最不好的，是吧？
刘老师那边肯定晚上很凉。对，你俩晚上肯定凉。
白天也不热。
白天现在也很热。
我在澳洲的佩西干谷，佩西其实白天的温度，但是晚上温度都能降下来。还有海风这个极有规律的，
看着非常的说的舒服，我看是从土长大的一个温度。
也没想象那么热，是吧？我觉得是没有我觉得。可能是这个每个人的这个适应度不一样。悉尼。
Welcome back. Now let's start the first session of this morning's plenary speech. Our first speaker is Professor Peter Goodwin. Peter Goodwin is the president of the University of Maryland Center for Environmental Science, Maryland's graduate university for the environment. He was a founding director of the Center for Eco-Hydraulics Research in Idaho. And he was a past president of International Association for Hydro-Environment Engineering and Research from 2015 to 2019. Peter is an expert in eco-hydraulics. Today, his talk carries the title of Balancing Ecosystem Recovery and Water Demands in California and Chesapeake Bay, USA. Now, Peter. Peter, please.
Right. Okay, I will just share my screen. Well, Professor Pengxi Lin, Professor Weilin Yu, President Joseph Lee, distinguished colleagues, good morning, and thank you for the invitation to say a few words this morning. I'm sorry we can't all be together, but I did want to emphasize the importance of this meeting. What we've seen in the last 18 months is when the world pulls together, how we can overcome through technology and management the COVID pandemic. This was an acute occurrence in the world, but we're facing an even bigger crisis. Water disaster mitigation, the effects of climate change. This is a chronic, more slowly evolving crisis, but it's also the most existential threat that humanity faces. So the importance of this meeting in bringing together the science and structuring that scientific information to inform management and long-term decision makings is critically important. And so in the talk this morning, I'd like to say a few words about the common challenges. It doesn't matter which continent you're on, but large-scale ecosystem management, the operation of the infrastructure, the recovery of the ecological values, protecting communities, is faced by every corner of the world, and it's made so much more difficult due to the effects of climate change. So I'm going to focus on two examples from the United States this morning. The first is the management of California's water, and the second is the Chesapeake Bay on the east coast of the United States. And in both of these instances, the managers, the secretaries, the directors of the water and environmental agencies are faced with making enormous decisions. Often it costs billions of dollars each decision they make. And they're forced to make these decisions in the face of often significant uncertainty. So I also want this talk to emphasize the value of networking. As academic researchers and researchers in research institutions, we do a very good job in meetings like this, in sharing information, sharing best practices, sharing new technologies and new techniques. But we should also look to see how we can help the agency leaders, those people in the very lonely position at the top, whether you're a river chief in China, whether you're a secretary of the environment in the US or the European Union. These individuals are faced with enormous challenges, and helping the networking, sharing how these difficult decisions can be made effectively, has to be made effective, best available science. So the drivers of complexity in large river basins, I'll talk more about climate change, but there's also other challenges, such as population growth, land use change, relative sea level rise in coastal areas. And often we're working in heavily stressed ecosystems where you get a catastrophic event, whether it's a flood, a drought, an earthquake, wildfire, can sometimes push those ecosystems over a tipping point into a new regime. And then the challenge of managing the system in this new regime, we can no longer use the historic record to make decisions. And of course, many of our systems, we're working with invasive species and emerging contaminants. But to start with climate change, in this beautiful rendition by NASA, this series of images were put together in March 2016. And if you look on the screen here on the west coast of the United States, this was the end of the 5-year drought. Absolutely no precipitation whatsoever. But for our friends in Northern Europe, you can see here the storm is just lining up across the Atlantic Ocean, and Northern Europe absolutely got hammered that year with extreme precipitation. And so these very small changes in temperature, particularly the warming of the Arctic, has many effects. And in the top left-hand corner, you can see the destabilization of the jet stream. This results in weather patterns that are outside the norms that we've experienced or see in the historic records. So while in California we were dealing with the drought of records, there's a little dispute about that. Some hydrologists say it was the 1 in 10,000 year drought. But in Northern Europe, it was some of the most intense precipitation, winter precipitation, that had ever been measured. And so we're all connected. And to look at put this in the context of this particular meeting, the water disaster mitigation. Since 1980, NOAA in the United States has been tracking water disasters that exceed $1 billion. So these are the really big events. And since 1980 here, you probably can't see all of the axes. On the left-hand side, it's the number of events experienced in a single year. And on the right-hand side is the cost of these events in billions of dollars. And the worrying concern here is you can see we are experiencing an exponential growth over the last 40 years in these extreme weather disasters. The UN and the IPCC have put out similar charts for the world. And so when we come to manage these large ecosystems in this rapidly changing environment, Millie and others at the USGS published that seminal paper back in 2008. And the first part of the title said, "Stationarity is dead." And why this is so important, it means that we can no longer rely solely on the past to predict future conditions, whether that's the expected flood risk, or whether it's how the food web within our ecosystem functions. So we need to be more sophisticated. The good news around climate change, I pulled this from a talk I gave a couple of weeks ago, and just in 2021, there's been a global outpouring of support that we really need to do something about climate change. So currently the presidency of the EU is under Portugal. And the president stated very clearly that climate change was going to be top of her agenda for the year. Similarly, I just picked out one other example here. President Xi and President Biden made a joint statement on April the 17th that committed China and the United States to work together and with other countries to tackle the climate change. So we are seeing a significant change, and associated with this is an increasing investment in the science and the technologies to understand this uncertainty. So with that, now let's turn to California. And California is on the west coast of the United States, of course. The figure on the left-hand side shows the precipitation map. And on that map, you can see most of the heavy precipitation in the state occurs in the north part of the state. On the right-hand side is the population density map. And that's the exact opposite to the precipitation map. So now with the shifting demographics, most of California's population lives in Los Angeles, Santa Barbara, San Diego corridor. To handle that, California has its north to south water distribution systems. The analogy in China would be, of course, be the south to north water transfer projects. But the important thing about this map is to realize that everything in California is plumbed, it's connected. So due to water rights, you can't do something in the north on the Oregon border without it having some impact on Southern California and vice versa. So California spends a huge amount of its annual energy budget just moving water around the state. If we go back to that figure just for a moment, you'll see that this is the Central Valley of California. This Central Valley drains from the north to south through what's called the Sacramento-San Joaquin Delta into San Francisco Bay. Similarly, the southern part of the state drains to the north, also through this delta area and out through San Francisco Bay. And this is a close-up from Google Maps. Here's the Golden Gate Bridge. This is the city of San Francisco. This is San Jose, Silicon Valley. And then the state capital, Sacramento, is over here. So now you're oriented. The drainage in the Central Valley flows from the north to south and through here from the south to north. And it all flows through this delta, which is an incredibly intricate system of channels that have been heavily modified over the last 150 years. This is another picture just re-emphasizing where the watering comes from in California. So the Sacramento River, 80% of the total inflow to the delta. 15% flows from the more arid south through the delta. This tends to be much poorer quality water because the southern part of the Central Valley is highly intensive agriculture. And the other important thing to note in this figure is that all of this is in a tidal region. So the water is saline in the bay, it's fresh in the upper parts of the delta. So an incredibly sophisticated and complicated system of channels. The diversions to take water south to Los Angeles occurs in two systems, the State Water Project and the Central Valley Project. One is the federal project, the other is the state of California. Ideally, you would take the high quality water, pass it through the delta as is shown here, and then pump it south. But it's complicated. The San Joaquin River flows from the south to north. This is the poor quality water. And when these pumps are really operating, it actually draws water, so water flows upstream towards the pumps. Now imagine you're a fish or some kind of species that is dependent on the flows. You can imagine the difficulty in navigating through this complicated system of channels. But the problem gets worse. The whole delta is levied, and over time this area has been subject to heavy agriculture, groundwater pumping. So this system of large islands have subsided to the point of now being 12 to 15 meters below sea level. So these levees have water against them 24 hours a day, 365 days a year. To give you an idea of scale, if you were to be in the Netherlands and were to go from Rotterdam to Amsterdam, you would have only traveled about 2/3 of the way across the California Delta. But the problem gets more complex. This is a seismic area. It's an area subject to earthquakes. And currently, the expected 6.5 earthquake is about 200 years overdue. So these levees, which were built, most of them in a non-engineered fashion over time, by farmers. If this earthquake was centered on the delta, there's a very high probability that many of these levees would fail. And this is a simulation by a colleague, John DeGeorge, with RMA, UC Davis. And this shows what would happen if 20 of these large islands had levee breaches. And the simulation shows that in less than 1 month, this land, which is currently 8, 10, 12 meters below sea level, would fill. Where would that water come from? Well, the rivers aren't close enough to being able to fill that kind of volume. So water would be drawn in from San Francisco Bay and the Pacific Ocean to fill these areas, and it would be saline, as is shown in this simulation. And this is the main drinking water supply to the major cities in the south of the state, it's also the major source of irrigation water in the Central Valley. So the problems facing California are enormous. 2/3 of California residents rely on water that comes from the Delta. It irrigates over 16,000 square kilometers of California farmland. It's incredibly biodiverse. It's globally recognized as a hotspot for biodiversity. But because of the stresses on the ecosystem, it's also internationally recognized for the greatest loss of biodiversity. And then on top of that, California has the greatest variability of precipitation in the United States. And when this precipitation does come, it tends to come as extremely intense rainfall. And some of the most intense rainfall measured in the United States is in the Bay Area around the Delta. This just shows the huge variability in California's water supply. And typically, as hydraulic engineers, we're trained to consider an average year, as is shown here by the yellow line. And what California has learned in the last few years, that you can't manage California's water based on an average year, because as this figure shows, the average year never happens. It's much more realistic to manage the water for some base level, as is shown here in the red line, and then a surplus, which depends on the number of these intense rainstorms or atmospheric rivers that are experienced in a given year. And I mentioned too the ecology. The ecology of the Delta, because it's been so altered, is on the point of collapse. This is just one species, the Delta smelt. And this is used as an indicator species, because if this species survives, we know that many other things within the Delta and the estuary will be good. But the difficulty is, if we manage the water inflows for temperature, for water quality, for the Delta smelt, as an earlier slide showed, there's something like 700 species. Many of these species are managed by different agencies. They have conflicting requirements. So the problem is, who decides? And then on top of that, I mentioned briefly the drought of 2012 to 2016. This was extreme. To give you an idea of how extreme this was, the snowpack in 2015-2016, if you took the lowest ever snowpack recorded in California, the snowpack in that year was 1/3 of the previous lowest ever. This meant that agriculture in the Central Valley received 0 surface water diversions for 2 consecutive years. So you can imagine the huge impact that had on the agricultural community. That was compensated by additional groundwater pumping. But the deficit in 10 years associated with this drought amounted to about 45 cubic kilometers of water. The consequences of that is that it created extensive subsidence in several areas of the Central Valley. The image here on the left-hand side is a well casing, and it shows the effect of groundwater pumping. This here is 1925. This is 1977, and my next graph will show how much more the ground has subsided since then. So you can imagine the impact this has had on irrigation, drainage channels, flood control, and many other issues. This is a graph put together by the USGS and NASA that shows subsidence in a 6-month period in 2014-2015 in the Central Valley of California. The colors, the legends there, go up to 300 millimeters. So there were parts of the Central Valley associated with this additional groundwater that were settling by about 300 millimeters in a 6-month period. So what's California doing about this? Recognizing the challenges of managing California's water across its more than 230 different agencies with some responsibility for managing the water, the state of California created what they called the co-equal goals, that legally in California, you cannot do anything to improve the water supply reliability without taking into consideration the restoration of the ecosystem. And the state set up a new agency called the Delta Stewardship Council to liaise, to work across the many different agencies, to organize the scientific information, to manage this immensely complex system. And to handle the uncertainty, it was recognized that with all of the technology we have, it's simply impossible to develop a predictive model that will tell you how the ecosystem is going to respond, how the economics of agriculture is likely to change over time. Because of this massive variability in the weather, the precipitation, and the shifts in the ecosystem, it has to be done, or decisions have to be made adaptively or continuously. So I would encourage anyone interested to go to the Delta Stewardship Council and read about their adaptive management plan. But the idea is you take the best available information, you plan, you then take management actions, but then you monitor very carefully to see if the outcomes are what you had hoped for at the beginning of the plan. If not, you go back, you make adjustments, and you keep cycling through this adaptive management strategy. And just for our colleagues in California, that 2016 drought ended with the wettest winter in recorded history in California. So it ended with very significant floods, and many of you may have heard the talks about Shasta Dam and some of the challenges associated with that massive runoff. But now California is entering a drought which could be even more severe. And this is a graph taken off the NOAA webpage. The legend on the left-hand side shows that more than 1/3 of the state is in the most exceptional drought experienced. And more, or 100%, is at least in moderate drought conditions. And here we are just at the beginning of July. So that was an example of how do you organize the scientific information to guide these huge decisions. So now we're going to move across to the east coast of the United States and look at Chesapeake Bay. Chesapeake Bay is another example of a large-scale ecosystem recovery program. It's the largest estuary in North America. Unlike the problems of California, it involves multiple states, plus the US capital, Washington, DC. And again, it's incredibly biodiverse, with over 3,000 species of plants and animals. So, going back a little over 20 years, the states realized, and the federal government, that the water quality in Chesapeake Bay was degrading dramatically. And two programs were put together, the Chesapeake Bay Commission, that is run by the states, and then the US Environmental Protection Agency established the Chesapeake Bay Program that has both a regulatory function plus a responsibility for organizing the science to inform the process. So the challenges around Chesapeake Bay is that it has a very large watershed. So the catchment is very large. It has a very large surface area, but it is incredibly shallow compared with other major coastal estuarine systems. And this chart just gives a few of those examples. So because the average depth is so shallow, Chesapeake Bay responds extremely, it's very, very sensitive to warming, for example, and there isn't the same volume of receiving water to absorb the contaminants and pollutants that come into the bay. So for this reason, it makes it a very interesting example on how this restoration could be achieved. Like many of the systems that you work in, there's very diverse land uses, transportation corridors, natural wetlands, agriculture is very significant, livestock throughout the watershed, there's some timber extraction. Also, it's renowned for its recreational yachting. It's the sailing capital of the world. And of course, there's several major cities dotted around Chesapeake Bay. Baltimore City and Washington, D.C. are two of the largest. So back in the early 1990s, the water quality of the bay had really dropped significantly. So the figure on the left shows the condition of the bay in July 2004, after this program had been running for a few years. And more than 1/3 of the entire volume of the bay was considered to be a dead zone. A dead zone means that the dissolved oxygen was so low that fish, crustacea, simply could not survive. So a restoration goal was set to improve water quality and bring back some of the living resources of the bay. To do this, the logic said that to achieve this, dissolved oxygen should increase, the clarity of the water should improve. And so there were very specific targets set out. And through the efforts of the US Environmental Protection Agency, this is just a summary of that the symptoms that were experienced, whether it was fish kills, harmful algal blooms, all of these consequences were thought to be caused by excessive nutrients, particularly nitrogen and phosphorus, and additional sediment loading. There was also loss of natural areas, over-harvesting of fish, and of course the increasing urbanization of the bay. So a very concerted program was initiated across all 6 states and within Washington, D.C. to reduce pollution with legally established targets to reduce the sediments and the nutrients. So it included air deposition, it included septic tanks, as you can see here, massive upgrades to wastewater treatment plants, stormwater runoff, urban runoff were all taken into account. This is a graph to show the implication of the Clean Air Act that either shut down many of the fossil fuel power plants in the Midwest upwind of Chesapeake Bay. And the drop has been quite dramatic. So either those power plants were closed or scrubbers were installed on the smokestacks. And coupled with very detailed monitoring, the drop in both sediment and the nutrients has been quite dramatic. So this is really seen as an example of success. But now, what's interesting about this, the question was then asked, the total maximum daily loads, the EPA imposed standards to reduce the nutrient loading and sediments. If we achieve those goals, will the overarching objective of these actions to bring back the wildlife, to reduce harmful algal blooms, all of those initial goals that were set out, are they achieved if we meet these nutrient reductions? So for the last 2 years, there's been a very comprehensive analysis to try and answer that question. And of course, it's not simple. So this is an example of the loop being changed, moving from public policy, where politicians realized we needed to improve the environment. Most of this was driven by poor water quality. That resulted in water quality standards being set by the Environmental Protection Agency and the total maximum daily loads. There were then policies implemented by the various states and Washington, D.C., where each state was allowed to decide how they would achieve their allocation to reduce nutrient loading. And each state monitors their progression. And as you can see in the bottom right-hand corner, if you follow this graphic around from across the top, so now we're having success in the reduction of the nutrients and sediments. We're also monitoring the water quality response. Are we seeing greater clarity? Are we seeing less harmful algal blooms? But we're beginning to get a handle on that. But how have the living resources, which is where the original program started, how are we doing in those areas? And this study is targeted to be wrapped up in December this year to see on this level of scale, are the original objectives truly being achieved? And so I'd like to just finish with a couple of other comments. If you go back and you think of what the California Delta looks like, what we realized in a paper in Bioscience, we were asked to define what the natural flow regime for the Delta was. And the outcome of that paper was there is no such thing as a natural flow regime anymore. Because even if you moved all of the people off the landscapes, you took away all of the levees, if you took out all of the dams, all of that plumbing, you would never restore the historic flow regime because there have been too many irreversible changes. So if we're trying to manage the ecosystem, we have to start thinking in a different way. We can't talk about restoring something where we simply cannot get the physical conditions back to achieve that. We have to start considering novel ecosystems and decide what are the critical functions from the historic system that we need to sustain in order to keep the food webs and the critical species surviving under climate change. And the second thing that Dr. Moyle pointed out, the famous ecologist at the University of California, Davis, it's no good just having a resilient or sustainable ecosystem, because you could have a very sustainable ecosystem that is totally full of invasive species or undesirable species. So we have to begin to start thinking about what do we want and how do we develop those predictive ecology tools to ensure that we're on the right track. And the final point I wanted to make was around in environmental intelligence. When we have the models, when we have the data, how we actually communicate that so that the secretary or the agency director or the minister that is making decisions can communicate the rationale behind his decision to society, to the cities, to the local governments. And this is a wonderful example. The update of the Chesapeake Bay report card for 2020 was released just last week. And I would encourage you to take a look at that, of how the science and the conditions in the Bay is linked to what's important to local communities. And so with that, I'd like to thank you for your attention. And just to state the obvious, managing these large ecosystems are incredibly complex and dynamic. They're changing very, very rapidly. We're seeing different weather systems, different types of storms. In order to understand this, it takes a sustained interdisciplinary team science to unravel the complexity. We need to be deploying new sensor technologies, whether it's satellite or drones or in situ sensors. And the final thing to say, just on behalf of the science communities of California and Chesapeake Bay, the value of engineering, scientific, and leadership exchanges around these large ecosystem challenges are just immensely important. So with that, thank you so much for your attention, and I wish you all a very successful meeting, and sorry that I couldn't be with you in person today.
Thank you, Peter. And I think we still have time for a few questions. Anyone who want to ask question for Peter on his talk just now? Yes.
Hello, Professor Peter. You gave us a very interesting presentation. Maybe in your first slides, you show us a figure. During the past more than 100 years, different disasters in California. But different kinds of disasters, the storm, floods, storm surge, and so on. But the figure showed in 2020, a lot of storm events, but totally no floods. What's the relationship between storm and floods? I cannot understand why not of storm but no floods in California.
Okay. Well, thank you for the question. Let me just go back to that slide. And this is beautifully documented actually on the NOAA webpage. So I think it's, what you're seeing, first of all, this is the, sorry, I'm having trouble pulling that up. But I think, first of all, that graph is showing the weather and climate-related disasters for all of the United States. So under that, there's different types of storms. There's the tropical storms, the ones which would affect coastal flooding. And then there's also the intense precipitation storms, not in 2020, but for example, the severe flooding in Texas that we saw. So that was a precipitation event that created both pluvial flooding and river flooding. So if there was no river flooding in a particular year, it just means that the damage created by that flood did not exceed $1 billion US. So it didn't mean that there was no floods that year that created damage. These are just the very, very big disasters that occur.
Thank you, Peter. This is there's an online broadcast, so we have a question from the web who cannot come in person. The question is, ask your opinion on large dam construction and the impact on the ecosystem. There are a lot of large dams in China and also probably in US. So what's your opinion about that?
Yeah. So, well, thank you, Professor Liu, for that question. And actually, it's a very good question. There was actually a talk in the IHR forum today around dams and the aging of dam infrastructure. So the question is actually very complicated. Maybe I'll answer the question just from the point of view of climate change. In the US, under President Clinton, there was a decision the big dam building was over. But what we've been seeing in the last few years is the value of dams and the water infrastructure, not just for mitigating against the droughts, which is absolutely critical, but by looking at ways that large dams can be reoperated for environmental benefits. So, for example, in the northwest of the US, stream temperature is becoming critical for many species. As the water temperature increases, if you look at salmon, the metabolic rate of the fish goes up, and the fish actually has difficulty making it from the ocean to the spawning grounds. So it's possible to use the cold water pool in those large dams in order to sustain the migration corridors of, in that case, the salmon. So what these large dams do is perhaps give us more flexibility in balancing water supply, economic growth, water supply reliability on one hand, and balancing some of the adverse effects of climate on the other. But at the same time, I don't want to diminish the fact in the Columbia Basin, the fact of those large dams. Even at the time, it was known that many of those salmon species would be unable to survive. So we recognize the environmental impacts and implications of these very large infrastructure projects. But there's also benefits. And I think this is just an example of making the trade-offs, the very difficult decisions that the minister, the agency director, needs to make. And so really, the answer is it's very, very site-specific as to the value of the dam, the various benefits that you get out of it, the flexibility that you could perhaps have to mitigate and offset some of the consequences of climate change, and perhaps allowing species the time to adapt to warmer water temperatures or different hydrologic regimes. But it's a great question, but
thank you.
You could have an entire conference on that.
Yeah, thank you. We still have time to take one last question. Yes, please.
A very interesting topic. I'm Wei Yang from Sichuan University. Just one question. On one slide, you quote a sentence: resilient or sustainable ecosystem are not necessarily desirable ecosystem. I think it has a kind of philosophy taste. And could you explain more on what is the really desirable ecosystem? Thanks for question. Thanks for your reply.
Okay. Well, actually, it's a wonderful question, and I actually took that quote from Peter Moyle, Dr. Peter Moyle. And so the point was we were looking at the California Delta system, and we were trying to decide on the water regimes and the consequences of that to the ecosystem. And some of the challenges that you have, supposing you try and restore a very large intertidal wetland, and you create that, and then the plant species you hope that would be established does not take off, but there's an invasive species that comes in and totally fills that area. So that invasive species that outcompetes the native species might be very stable, it might be very sustainable, but it offers none of the ecosystem services that the native vegetation would have. So the point of that is it's philosophy, but you could perhaps have a very sustainable and resilient ecosystem that is entirely filled with undesirable species. And so what Dr. Moyle was encouraging us to realize was that there has to be more manipulation than just restoring the physical processes that had been there historically. And you just expect that, in that case, the tidal wetland function to be restored. So, yes, it was a philosophical comment, but I also think it's a very, very real one. And it also emphasizes the importance of adaptive management. What happens if you try and restore that part of the ecosystem and you end up with invasive species? If you haven't thought through that potential consequence and you're not prepared to react to that outcome, then you could have invested millions and millions of dollars for an undesirable outcome.
Thank you, Peter. And because of time limitation, we have to move on. Thank you again.
Well, thank you, Professor Lin. And good to see you.
Okay, our next speaker is Professor Philip Liu. Professor Philip Liu is a distinguished professor in the Department of Civil and Environmental Engineering at National University of Singapore. He is a member of National Academy of Engineering of USA. Professor Liu actually was my PhD supervisor at Cornell University. And to me, his training and mentoring during my PhD study is a lifetime gift. I really appreciate Professor Liu. And Professor Liu, his research covers those coastal hydrodynamics. Nowadays, when I already start to think about how to arrange my retirement life, he's still doing a cutting-edge research. So he's going to give the talk on the experimental study about the Bohr waves. Now, Professor Liu, please.
Thank you very much, Pansy. Hope you can see my screen.
Yeah, we can see it.
For some reason, I cannot see my own screen. That's a problem. I cannot see my own screen. I don't know why.
Maybe you should share the screen. We can see you, but not your PPT.
Oh, okay. How about now?
Yeah.
You can see the screen now.
Yeah, we can.
Okay. Oh, that's good. Thank you very much, Pansy, for the introduction. I'm flattered, and it's my pleasure to have this opportunity to participate in this conference. I must say that I was quite disappointed that I cannot actually come to the conference in person to meet with all of you. And I know that some of my old friends are in the audience, and say hello to everyone. Today I'd like to talk about a piece of research which was done by one of my PhD students at NUS, Ignacio, and he actually just finished a few months ago. And the topics is really to look at the borer propagations in the ocean, in the ocean, and also the swash flow process induced by these kind of borer. And so just to give you a general idea, the background of the motivation for this kind of research, basically, some of the tsunami, when they come to the shore, actually come in the form of undulating borer. This is a picture taken in Thailand during the 2004 Indonesia or the Indian Ocean tsunami. And so on the right here, you can see the undulating borer, and on the left, you can see the clear, very long crest borer front propagating toward the shoreline. And this is a video taken by aircraft during the 2011 tsunamis in Japan. And again, this is a very relatively long video, but what I want to show you is the evidence that these kind of tsunami can come in the form of a bore, a very long bore, with a breaking bore front propagating into the shallow water. Very soon you will see the bore front reach the breakwater and eventually overtops the bore. So the bore height at this point could be several meters already, all right, in the very shallow water. So the wave breaks very significantly. So overall, the scope of this PhD thesis or study is really trying to look at the possibility of deriving, deducing some kind of relationship between, say, the bore generated runoff high, and also inundation water depths near the shoreline, and also perhaps the duration of the flooding in the swash zones in terms of the bore strengths and bore lengths and bore characteristic, basically, and the slope of the beach at the center point of the incoming wave region, and typically will be in the more constant water depth region. And then also, not only just these kind of information like bore height, so on and so forth, we would like to have a chance to study more carefully about the velocity field underneath these kind of bores, and both in the constant depth region, also in the swash zone. The purpose of that, obviously, is not only understand the fluid dynamics of the province, and also perhaps that will help us to understand some of the sediment transport phenomenon associated with tsunami propagation or tsunami inundation in the coastal regions. And so I must say that some of these results has already been published, as you can see that in the GFM paper recently. If you are interested in the details, please find this paper. And so I will go through it pretty quickly. Also, the first part of the talks, talking about the runoff heights, inundation depths, I have already given another talks in the Coastal Lab 2020 in the Zhousan meeting. So the new stuff I'm talking about today, I will include the so-called velocity measurements part. But I will still mention something about the inundation depth results, right? Just to give you a complete picture of the whole process. So the way we carry out the research multi approaches. We do have a good facility at NUS, laboratory facilities. So we will do some laboratory experiments and measuring some of the relevant parameters and to try to help us to understand the process, that including the surface elevations and also the velocity by using the PIV methods. Then we also take advantage of the fact that there are existing numerical models which can be used to simulate the process, including the breaking. For example, the swash, which is multi-layer hydrostatic models simulating bores or other kind of long wave in the surf zone or swash zones. And the purpose of that is really trying to use a numerical model to produce larger sets of data which covers a wider range of physical parameter such that we can deduce more general conclusions. And in the process of that, we also use some analytical tools such as method characteristics. Okay, so this is just a quick overview on the facility we have. This is the wave flume we use at NUS. Dimension is 36 meter long, roughly 1 by 1 type of cross section is 0.9 by 0.9. And there are two wave bore generation mechanisms we have in this wave tank. One is what we call the dam break system. And if you can see it, this is just a piece of a vertical bore, and that can be lifted up by the the electric systems and in a very, very fast speed. So you release the water behind the dam and create a bore. Well, I will show you some videos later on. And another method to generate bore is a more traditional, well, the so-called wave maker systems. And in this case, we happen to modify our system so that we have a relatively long stroke. It's a 5 meters long stroke, which enable us to generate much longer bore. I will show you later. So this is just a sketch of the setup for dam break system. As I said, this is just a vertical piece of wall, and that can be lifted up by an electric system, trigger it, and then we can lift it up. Then behind it is a so-called reservoir, and we have a back wall set up here that can, so that we can adjust the capacity or the length of a reservoir, and that gives us the ability to generate different bore length and also bore strength. Okay, and on the beach here, we have 1 on 10 beach. That's a limitation of physical laboratory experiments. Usually we cannot afford to use many different kind of slope to do the experiments. On the other hand, when you have a numerical model or trustworthy numerical model, then you can vary the slope easily and then can look at the feasible slope on the physical parameters you are interested, variables that you are interested in. Likewise, and the location of the bore, distance between bore and the toe of the beach is also fixed in this experiments. So these are the parameter range for different water depths, therefore give you different depth ratios, which will produce different bore strengths. Then we have different kind of wave gauges and to measure the free surface elevation or PIV to measure the velocity. Okay, so again, this is the wavemaker setup sketch. As I mentioned, that the stroke of the wavemaker is 5 meters. That's a maximum stroke, and you can push the stroke wavemaker again in a control manner. We have electric systems you can accelerate the wavemaker at different accelerations, and then again we can vary the water depths and to change the stroke and the speed to have different kind of a bore being generated, basically including the so-called undulating bore and the breaking bore. And for this set of experiments, we did manage to get two locations, the field of view, we call it, to measure the velocity in detail. And one of the limitations of a wave tank is that the wave channel, the wall of the wave flume is not all glass wall, so only limited section places that we can put in used to take PIV measurements, right? So that's somewhat limitations. So quickly, just show you how this wave dam break system works and what kind of wave you can generate. So basically, it's a simple mechanism. The trick is that you want to lift the gate up quickly, as quick as possible, and vertically, so that generate little disturbance, right? And then this is a wave maker systems, and you can see that again is a pedal pushing forwards at a certain speed or accelerations. Then it will generate the different kind of bore. And this is a close-up shot look at the swatch zone, but not entire swatch zone, but at least a wave coming in and run up the slope, that 1/10 slope. So this is a long bore, and so the bore just keep coming, and that's typically the phenomena you see in the tsunami, the real world situation. And now it's receding. Then this is different one is undulating bore. Okay, so this is more or less mimicking the picture I showed you at the very beginning. All right. So the goal here is really to measure the run-up heights and also the inundation depths and the duration of the flooding in the otherwise originally the drylands area. Then also we want to measure some velocities. Now you probably know this that when you have a long bore, in the constant water depth regions, that bore can be described by the so-called nonlinear shallow water wave equations, and then you can describe the bore propagations by the method of characteristic. This is simply showing you some definition of bore strength and the ratio of the water depths before and in front and behind the bore itself. Okay, so there is, based on the shallow water wave theories and the method of characteristic, you can more or less describe the bore propagation in the constant water depths in an analytical way. And the next couple of slides, I'm just going to show you some of the data we took, and for both undulating bore and the breaking bore, using the different kind of mechanism to generate them. This is the dam break generated bore, and you have undulating bore on the left, and you have this kind of breaking bore on the right. So the weaker bore strength will generate an undulating bore. When you increase the bore strength, you tend to have a breaking bore being generated. And again, for the dam break system, the bore length can be changed if you have a different kind of reservoir length. All right, so these are showing typical different kind of a bore length. And again, using the wavemaker generators to generate a wave, and you can generate a very similar bore. Actually, it doesn't really matter what kind of generation mechanism you use. After you move away from the generators, and the bore will actually becomes very similar. Again, on the left, you have an undulating bore, and then you have a breaking bore for the different bore strength, right? Now, as I said, I show you that use the method of characteristics and with the nonlinear shallow water wave, you can derive the relationship, the characteristic of the bore. And this is simply showing that in the laboratory experiments, when we do the measurements, and you can confirm that indeed it's true in the laboratory setup. we have for both systems that when the bore is propagating in the constant water depths and nonlinear shallow water wave equations and the method characteristic can predict the bore characteristic very well. So these are the data compared with the theory, basically give you the same thing. Now, for the wavemaker generated bore, we have another unique situation. That is to say that we can generate a relatively short bore in such that when the wave, the bore actually is still in the constant water depth region, the bore, the plateau or the crest actually has already approached to zero. That means that the bore doesn't have the crest anymore or the plateau anymore, and then the bore strength is start to decrease. So for that kind of bore, the method of characteristics cannot really predict in the same way. So this is showing you basically that when you compare the bore strength at the beginning near the wavemaker and somewhere down the channels, and for certain bore length or the stroke length, and the bore strength is start to decreases. It's not following this straight lines. Okay, 45-degree line. Okay, so basically that confirms that the physical model or the laboratory setup can produce pretty accurate results, and furthermore also confirm that the bore propagation in the constant water depth region indeed can be described by the so-called nonlinear long wave theory, and the ANOVA solution deduced by the method of characteristic can do a decent job. And again, this is just the previous couple of slides showing the bore strength comparison. Here you show we show the depth ratio of the water depths in front and behind the bore front, and again as compared with the so-called analytical solution from the method of characteristics. If they're agreeable, they should be follow this particular straight line, and you can see that there is little data scattering when the bore strength becomes relatively large. But overall, the agreement is pretty good. Again, this is the wavemaker generated wave. Again, for the larger the bore strength, you can see some deviation. I guess those some of them actually is due to the decaying mode, a decaying bore, not a non-decaying bore. Okay. So when we're moving into the so-called swatch zone, and typically in the tsunami community, we are interested in measuring a couple of things, having some understanding of a couple of things. One is a tsunami runoff height, which is the maximum distance, vertical distance of the maximum the shoreline locations, and that's indicated by this quantity. Then you have this inundation distance, that's the horizontal distance from the stillwater shoreline to the so-called maximum runoff height. And of course, in between, you can characterize the tsunami by the so-called inundation height of tsunami heights or flow depths, inundation depths. Okay, so what we have done is that we measure the inundation depths at the stillwater level, shoreline level here, and also we measure the runoff height and also the duration of the flooding, right? Again, so this is the inundation depths measurements at the stillwater depths for the non-decaying mode during the Danbury problem. And you can see that the undulating bore and the breaking bore behaves slightly differently because the front behaves differently. So the undulating still persists all the way into the swatch zones, right? Okay, so similar characteristics you can find for using the wavemaker generation mechanisms. Now, this is This is more or less the part of the results we have. That is to plot. We plot the inundation depths, all right, at the Stillwater shoreline versus the bore strength at the toe of the beach. Remember, we'll have the 1-on-10 beach. So the information at the toe practically can be considered as the information of incident bore conditions. And so the idea is that to find out what is the relationship between the inundation depths or run-up height on the right-hand side versus the bore strength, right? For this experiment, the beach slope is fixed 1-on-10, right? We cannot vary that, but the bore length can be changed. The reservoir length can be different, and therefore the bore length will be different. So this is for a Danbury problem. So one interesting observation is that as far as the run-up height is concerned, and the run-up height doesn't depend on the reservoir width or reservoir size. And also that means that it doesn't depend on the bore length at the toe of the beach. On the other hand, the inundation depth depends on that, okay? And especially depends on that when the bore strength exceeds a certain values, right? So that's a kind of interesting observations. And also then we'll get another piece of information that is the flooding durations also changes depending on the very much on the reservoir length or the bore length at the toe. So that triggers our intrigue us. We say that, well, the laboratory experiments shows this with a limited parameter range, namely the slope is fixed. And also this plot is presented in terms of the reservoir length alone, right? So we decided to do some numerical simulation by varying the beach slope over a certain range, and also we translate the reservoir size or the length of the reservoir to the bore length at the toe. So everything, all the input parameters now is represented by the characteristic of a bore at the toe. So basically, this is the idea. We want to express the inundation depths, the run-up height, and the duration of flooding in terms of the so-called incident wave parameters, and that is the strength of the bore at the toe of the beach, and also the bore length, right, and at the toe of the beach, and also the slope. And water depths and slope and the bore length can be grouped into the non-dimensional parameter. So we're looking after these relationship, and we do have a set of experimental data, but to establish these kind of relationships, we need to have more data. So those data are produced by the numerical simulations. Okay, so this is what we did. I'm not going to go into detail, I just don't have time. And we use a swatch basically, and change the parameters using different kind of slopes, so on and so forth. And basically we only use the dam break problem as a generation mechanism, because in theory, it doesn't really matter what generation mechanism you use. All we care about is obtaining the information at the toe of the beach, right? Okay, so without going into detail, let me just tell you the results, the story, okay? As far as the inundation depth is concerned, as you see that already, that from the laboratory experiments, it doesn't depend on the bore length if you have long enough of a bore. In other words, if you have a bore, the bore length is greater than this limits bore length, all right? And then the inundation depth is only function of the bore strength and the slope of the beach. But if the bore is not long enough, and then the inundation depth then will become is a function not only the strength of a bore at the toe, the beach slope, also the bore length itself at the toe of beach. So that is the empirical formula. We get the database is produced by the numerical simulations plus the laboratory experiments. We also use the laboratory experiments to validate the numerical model, to make sure the numerical model indeed is doing the mimicking the physical process correctly. All right. Now, on the other hand, the runoff height, it turns out to be independent of the bore length. Doesn't matter what kind of bore length you have, it's only function of a bore, the toe, the bore strength of the toe and the beach slope. Now, duration is similar of the flooding is similar to the inundation depths that has depending on the bore length, and as long as it's not long enough, and that is the relationship. Okay, so that's about it. And I want to say we have also the wavemaker generated bore, and will actually agree with the conclusions we make based on these kind of simulations as well. Okay, so I think I have a few, well, hopefully 10 minutes. I can go through some of the experimental measurements for the PIV. And so basically, we at 2 locations in the tank, when we generate the bore with the wave makers, and we set up a 1 location field view in the constant depths, another one is on the slope, all right, near the still water level. And so we want to look at the detail of velocity profile. And so for both undulating bore and also the breaking bore. The difficulty with the breaking bore is really the due to the breaking, you have this air bubble being entrained into the water, and that actually will create these challenges for using PIV measurements. And also, when you have a breaking bore, of course, there's aerated regions, and then that will actually block, will enable, we will not be able to measure any kind of accurate results, measurements using the PIV. Of course, there are other techniques can be used to improve, enhance the images and measure the velocities that I'm not going to talk about here. So all I'm measuring is underneath this area region, but it's not saying that this region is not important. It's a very important region. And I believe there's a very recent papers talking about precisely that. All right. And okay, so this is an undulating bore in the constant water depth region. And then these are the velocity profiles for the horizontal velocity, and this is vertical velocity. So this is at a fixed position, location, and at a different time. As you can imagine that this is an undulating bore passing you by, and you can see the velocity going forward and backwards, but the so-called backwards is not going in the negative direction. Actually, all the particles is moving forwards, okay? But it's just like the forward motion is usually bigger than the backward motion. And another characteristic, you can see that this is a pretty uniform in the entire water column for the horizontal velocity measurement components. And then the vertical velocity is a linear in the water column, and has 0 value at the bottom, of course. There's no flux boundary conditions. So this is a typical characteristic of long wave, the velocity field underneath the long wave. Okay, the uniform velocity in the horizontal direction and uniform in the water depth in the horizontal direction is a linear in the vertical direction. Of course, vertical velocity is practically almost 1 order of magnitude smaller than the horizontal velocity. It's a long wave theory, long wave problem. Now for the breaking bore, now you have to deal with the turbulence now. Breaking bore has a lot of turbulence being generated in the area of the region, and these turbulence is going to diffuse or evacuate down into the water columns as a bore propagating forwards. And so you can, we repeat the PIV experiments at least 7 to 10 times. So we are able to perform the so-called ensemble average and to find the ensemble average velocity and also the turbulence fluctuations. And then we can present some turbulence velocity field information in the ensemble average velocity. So very quickly, to show you again, this is in the constant depth region. All right. The left-hand side here is the map, and for the horizontal velocity, the right-hand side here is the vertical velocity. Again, the scale here is a little bit different. So the horizontal velocity is clearly much bigger than the vertical velocity. No surprises. It's a long bore. And what's interesting here is that if you look at the velocity profile in the water column, this panel here is the horizontal velocity. You can see the ensemble average velocity, all right, is almost uniform in the vertical column all the way to the still water level, okay? So this is the water depth in front of a bore, before the bore comes. And you can see the velocity actually is more or less uniform, but the velocity becomes larger when you get up to the surface. I think that is because the bore front is moving with a much larger speed, right? And again, the vertical velocity is practically one order smaller. Also has observed this kind of linear distribution profile in the water column, more or less. And then you can see some scattering near the surface because the turbulence effects. Right? Okay, so this is the ensemble. Let's see. Okay, so these are at a different phases. This is near the bore front. Okay, near the bore front here. Then the next picture is near the bore crest, and you can see this dimensionless time is between -30 to -25. If you go over this scale here, it's right around this region. All right. So interestingly enough, in this region near the bore crest, the horizontal velocity as well as the vertical velocity, to great extent, they are pretty uniform in the wave propagation direction as well. Right? So there is a very tiny little window here. The velocity field actually behaves like a uniform flow in space, right? Just that period of time, and they collapse into one curve practically. And the vertical velocity again is pretty noisy on the near the surface, and that's because of the effects of the turbulence. And again, this picture here shows you the velocity profile, horizontal and vertical, at the tail ends of the bore, and that is between -20 dimensions time to 19. So somewhere from here to here. Okay, this region here, as you can see that the profile is not uniform anymore. Actually, you can see that the more or less like a linear profile, then the very strong indication that the bundle layer effects shows up even in the PIV measurements. The vertical velocity is practically zero, right? Practically zero. So this is in the constant water depth region for the ensemble average. So let's take a peek at the turbulence field. It's kind of interesting to me that, again, I separated into the bore front and bore crest and bore tail. And this panel shows the horizontal velocity for the turbulent horizontal velocity intensity. This is normalized by the velocity celerity. And again, you can see that they almost collapse into one, all right? Even in the bore front directions here, you have practically zero, very small, the turbulence in the water underneath the still water level, in the water column underneath the still water level, then shoots up, becomes very large due to the influence of braiding. Okay, and now the vertical turbulence velocity, and interestingly enough, in most of the places, actually the order magnitude is about the same. Right, so you can say that it can. Well, we're analyzing more carefully now is whether that means that this is isotropic turbulence in this region or not. Right, we're doing some other analysis, turbulence flow analysis, looking at the spectrons and also the integral lengths, so on and so forth, to characterize turbulence more carefully. Okay, and so now near the ball crest and in this narrow region here, and for all practical purpose, they are following pretty much a similar kind of trend, and the differences are quite small. And again, the vertical turbulence components again seem more or less in the same order of magnitude. It's not that much smaller than the horizontal turbulence velocity. And in the ensemble average fields, that is quite clear. The horizontal velocity is much, much bigger than the vertical velocity, right? So this is during the tail ends. Of course, everything sort of died down a little bit, but interestingly enough, you can see that to look at this region here, the order magnitude is 0.02 when you get down to the bore tail, and it still maintains similar kind of a level of turbulence, and in fact, the overall turbulence distribution in the water column becomes more uniform. That's not too surprising because the bore front has already passed. No more braking generated turbulence near the surface. All right. Okay, so this is the in the swatch zone. Let me go through this very quickly. So this is the surface profile looks like, and also including the ensemble average velocity, and in the horizontal direction. Actually, this is not horizontal direction. This is direction along the surface of parallel to the beach surface. And then capital W means is the normal to the beach surface. That is the orientation measurements of the PIV we did. Okay, so oscillatory behavior still remains. And then if you look at the profiles at the different locations, I didn't plot that many of them. The circle is near the crest. And then the second one is 17 and 19. And so this is during the first wave, okay? First undulations, and you can see the behavior of the horizontal velocities and from large to small in that sequence, and then forwards again, okay? And it's still more or less uniform in the entire water columns, right? The vertical velocity is much smaller, and then has a somewhat kind of a linear distribution behavior, even in these regions. Again, this is a jump over the tail end of a bore. You can see that the ensemble average velocity started going backwards, and because the rundown process has already started, and vertical velocities remains relatively small. That's ensemble average velocity. The turbulent velocities is kind of messy, a lot of scatterings. And again, the order magnitude of the horizontal turbulent velocities and the vertical turbulent velocity are pretty much in the same order of magnitudes, all right? And again, if you look at the scattering, avoid the scatterings, you can see some turbulence being generated perhaps in the bottom friction, and also some of it definitely is coming from the surface. All right. So this is during the board tail, and again, some kind of uniform structures in the water columns is quite clear. Okay, so that's the undulating bore, and then we have this kind of breaking bore. When they get to the swatch zones, the shape of the surface looks kind of very smooth and without undulations. And basically, you have a run up and a run down in terms of velocity orientations. Right, the blue one is uprush, and the red one is a downrush. So you have uprush phase and downrush phase. And again,
sorry to interrupt. Probably you want to wrap up quickly, so we have time for questions.
I think this is almost the last slide. So this is simply the horizontal velocity, ensemble average velocity, and again, just look at the features. It's pretty uniform in the vertical directions, and the vertical velocity is much smaller. Okay, and then there's near the plateau, and you'll have a velocity started turning downrush, right? And turbulent field, I guess I don't know what to say because it's pretty noisy, and except that the order magnitude of the horizontal turbulence and vertical turbulence are still in the same order magnitude. Okay, as I said, we are still in the process of analyzing the turbulence data more carefully, and so we have more insights on the turbulence characteristics, and especially in the surface zone. That's what we really would like to know. And sorry to run over time. These are the general conclusions, and the first part, of course, is the characteristic of the run-up and the inundation, their dependencies on the bore length, and the bore strength at the toe are clearly presented. And then we are able to get some velocity data. And I think once we analyze the turbulence field more carefully, there will reveal some a lot more insights about the turbulence dynamics in the swatch zone. The difference between the undulating bore and the breaking bore probably are quite different, right? Okay, so that's all I have, and thank you very much for listening. Be happy to answer questions if I have time. Thank you.
Thank you. We will still have time to take a couple of questions. Quick one.
Hi, Professor Liu. I'm Zhiping Huang from Chongqing Institute CAS. I'm very interested in this topic, and I noticed that the shallow water model was applied. And I wonder why you select this model. Is there any comparison result among other hydraulics models? Thanks.
Well, that's a good question. Of course, you can try to see whether you can use, for example, Boussinesq equation, or the shallow water wave equation basically assumes that there's no dispersion, right? And we look at, we take the swash model, although it is non-hydrostatic, and so to a certain extent you can say that has some kind of a dispersion effect in there, but we didn't explore that aspect very carefully, and we checked the method of characteristic, which is definitely shallow water, non-linear shallow water, no dispersion. It sort of fit the data pretty well, so we sort of just go with that particular model. But it's a good point. One could explore that to see whether dispersion effects becomes important or not, especially you start to think about the shorter bore. With a longer bore, I have no doubt the long wave definitely works, theory works. But when you have a shorter bore, and even in the decaying bore, there may be some dispersion effect becomes more important. Maybe that's why we have more scattering when you compare with the compare the data and numerical results.
Okay, any other question? Yes, please.
Thank you, Professor Liu. I just have a small question. I noticed that in your flume test, there's the slope is quite smooth. Probably
Yes.
the bottom of the flume is the same. So did you consider the roughness of the bed in your study, or you think it is negligible? Thank you.
No. That's an obvious concern, right? I think in the physical, more field work and in the field situation, the beach definitely is not smooth. So the roughness effect definitely should play a role. Now we did a laboratory experiments, and using the smooth surface is much easier to control. To be honest with you, I think somebody probably should take a look at carefully about the roughness effect and see whether that can be included in the formula, the empirical formula. And the question is that how do you characterize the roughness in the manageable way to be included? Basically, I agree with you. Roughness probably should be considered eventually if you want to apply this to practical problem, and maybe somebody can pick it up and to work on it.
Last question. Yes.
Hello, Professor Liu. This is Xiping.
I can't see you. So.
Nice to see you online. Asking questions is a good excuse to say hello. So my question is actually a small question. Is there any basic difference between a bore generated by dam break and a bore generated by a wave maker if the intensity of the bore is the same?
Question is whether there's a difference between these bore generated by two different mechanisms, right? Is that hello?
Yeah, that's a question.
Okay.
Yes, that's my question.
Right. No, theoretically speaking, it shouldn't. And but the theoretically meaning that if you can get away from the generation region, there's always this generation region, right? And then because the generation is always have some local disturbance. But if you can move away from that we measure the wave bores generated by these two mechanisms, theoretically it shouldn't have any difference.
Okay, Professor Liu, and I have one message and one short question before I close. The message is from Professor Tan Yiji from National Taiwan University. He's online. He asked me to send a greeting to you. That's a message. And the question is that the run-up height based on the empirical formula you provide is linearly proportional to slope. I'm wondering whether this can be applied to a steep slope, because I can see if it's vertical wall and the solution will blow out.
That's a very good question. And when we do this curve fitting, and we basically use a so-called, what's the jargon for that? Is a linear approximation. For all the parameter, you can, if I can move this, I cannot move this anymore. Yeah?
Yeah, that's the first question. First, the formula.
Yeah, you can see even for the bore strength is linear, right?
Yeah.
All these is linear. So this approximation is that when you have this whole bunch of data in the space, the parameter space, right? You have to do a curve fitting, and well, I guess this is called a bilinear approximation or something like that. But you're right. You can improve this curve fitting by consider some S to certain parameters, a certain power, or even for a number to certain power. But I guess what the reason to justify the validity of this is looking at the picture on the left hand side. Okay, so basically, these are all the symbols are data. Okay, and all the straight lines are these empirical formula, and for the different sets of parameters. In other words, for example, R for the run up, and if you fix S, then this is all the data we have, and you plot against the ball strengths. Indeed, can be nicely fit with the linear curve. Now. I guess what you're saying is if S becomes very large, what happens, right?
Yeah.
Oh,
yeah. If it's vertical, then it's go to infinity.
Yeah, but I guess we don't have that data.
Okay.
Yes,
anyway, thank you very much. We will think about this, and thank you again. And we will close the first half session of this morning, and we will move to the tea break.
All right. Thank you very much.
Thank you.
Bye-bye.
I think for the tea break, maybe we'll have 5 minutes extension, and we will come back at 11:05, 11:05. 我们准备的这个茶歇，质量很好，但数量不多，大家要吃就赶快哈。
那你就给多少名吧？这个你跟他打。
是吧？
都在。
所以先第一个，就我们把我们的建议解除掉，把他应该。OK，
我不是很熟这个东西。
Hi, I guess I don't know if you guys can hear me. I need to talk. This is David Zhu. I will be hosting the second session. I'd like to chat with Professor Granchi Kalonji. I don't know if you can hear me. If you can, maybe you can unmute. Or maybe not. Okay.
No.
Or Professor Toshio Koch. Or he'll be transfer. Any of you are online? Any of you online?
I think this should be all online. 或者我们打字呢？打字给所有人。
Yeah, sure.
Yeah. No, 05. 05. Yeah.
就到时候是40分钟加5分钟的。
没有，一共就是40分钟了，一共就是40分钟。
那你告诉他们的。
他们知道，
他们都知道。
一开始就是通知了40分钟。
这里写的45分钟。
对，后来就是后来为了您这个是您这个是打印出来的，后来他下面贴了更正，把 photo 提到前面去了，就变成没事，他们都知道。
都知道。
对对对。
那40分钟里面，你觉得给他们多少时间的提问呢？还是说？
我觉得让他们自己控制吧。
如果超过了呢？你看不看？
有备就是
就关他了。
最后的有备的，他把他的录的视频发给我了，差不多就30分钟。然后那天跟卡隆他们两个。
你的他的名字怎么读
？Toshio Koike。
差不多，这个是日文发音吗？
对对对。
真的。
你好。这是什么？
这是确认今天的会议室。
好，谢谢。
他在。
来了。
说，那你把它开起来。
Hello。
Hi。这是下面的会议室。
这个还得。就估计这边你还是回音在里面，你还能把它开来。行这边在了是吧？
对。
那你怎么办？能开吗？还是不能开？算了。就没法跟他们交流一下是吧？不常回应。
刚才是我们的回应吗？
对，刚才是我们的回应。
那就
肯定另外一个行，那就算。那现在我再回来吧，再倒回来，打个档。 那行不管了。
好，好，徐老师。
等会坐哪里？这个位置。
您看哪个地方？行。空着。
喂喂喂，这个话筒。Hello Hello Hello。
Hello Hello。
OK。我们开始下一场的了，因为时间有点紧张大家是不是回来了？不知道用哪一个 ？Mic on right？ 对，是应该是 on 的是吧
？Start sharing screen。
我们大家回来啦，我们下一场开始。关键就叫外面的人回来。喂，我们开始下一场吧。要么外面有没有人通知一下？ All right, so I guess we will just get started. So my name is David Zhu. I'm chairing the second part of this session. In this session, we have two speakers. The first one is given jointly by Professor Granchi Kalanji and Toshio Koki. The title of the talk is on multinational models for collaboration on water disaster mitigation. Just quick brief introduction on Professor Kalanji. She's the Dean of the Sichuan University and Hong Kong Polytech University Institute for Disaster Management and Reconstruction. Prior to this, Professor Kalanji served as the Assistant Director General for Natural Sciences at UNESCO, and she also worked for University of California and the University of Washington. Professor Toyashi Kawaki is a director of International Center for Water Hazard and Risk Management of UNESCO. He is a professor emeritus of University of Tokyo, and his research interesting mostly on water cycle and climate science and the applications. Okay. Okay, so we can get started. Okay. You are muted. You probably, yeah, you unmute.
Sure.
All right, great, thanks.
Hi.
Slide, maybe.
Really. Hello, everyone. I'm really happy to have this opportunity. I'm going to move my slides up right now. Can everyone see my slides?
Yes.
Okay, great. So what I wanted to say is that it's really an honor to participate in this session and to work together with my colleague, Professor Koike, on this. I mean, our topic is a bit different from others in that we're primarily focusing on how to make multinational collaborations work. Everybody's doing great work, but how can we work more effectively together? And so I will begin by talking about some of the existing models of collaboration. You know, there's the broad theme of water and the broad theme of disasters. They intersect, of course. And in terms of international alliances, there's international scientific programs, university alliances, other platforms, youth initiatives, initiatives by professional societies. IADR is a wonderful example. But there's some critical missing elements in our opinion. And then I will move on to introducing the work of the high-level panel of experts and leaders in water and disasters, and turn it over to my colleague, Professor Koike, to give some more specific examples. So again, what are the existing alliances and networks? Some of them are regional in scope, others are global. Some focus on sub-themes like drought, and some focus on more broad themes. And so some of the existing alliances, of course, we have the IHP. Having worked for UNESCO, I really appreciate the work of the IHP because it's got, 169 national committees around the world, 36 research centers, including the one headed by Professor Koike, 66 UNESCO chairs, and multiple initiatives. So UNESCO is very important, but of course other UN agencies are also important in the area of water. In fact, when I was at UNESCO, I think there were 49 UN agencies working on water, including the Outer Space Agency, looking for water on other planets. So it's very, very important. And then what is often neglected in our scientific community is that we already have existing alliances among disaster research institutes. The oldest is GADRI at Kyoto University, already has 200 member research institutes around the world with sub-institutes, including the most recent one in South Asia, SADRI. So if you're not members of that already, I encourage you to take a look at GADRI. GADRI is very important. And then, of course, civil society. We have the Global Water Partnership, which is a huge organization bringing together civil society and other partners all around the world. We have the World Water Council, which is very effective on bringing together the private sector, which is often neglected by us academics. And then we also have the International Research on Disaster Risk Program, which has major efforts in water and disaster. It's co-hosted by UNDRR and the International Science Council. And I would say the World Federation of Engineering Organizations has a very important disaster working group. And lastly, we need to make better connections with the WHO. And they're doing a lot now with water and health. In terms of university alliances, there are very, very many. One of the most impressive, in my opinion, is the African network of universities called PeriPeriU, which actually has linked multiple African universities on disaster risk education and research. And then, of course, there's also the Association of Pacific Rim University as a multi-hazards working group. The Himalaya University Consortium, that's a regional group that we're heavily involved with, that links the 8 countries in the Hindu Kush Himalaya. And UNU and other partners have been working on a network called ProsperNet to promote sustainability in graduate education. So we have all of these bodies. So the challenge is, can we do a better job in bringing them together? So the challenges, in my opinion, are we still have not done a very good job on bridging the science policy interface. So we need to do that at local levels, national levels, regional and global levels. How can we do a better job in the broad area of water and disasters? The other critical question is our higher education systems. If we don't transform our systems to be more effective and more creative, we're going to be doing the same thing over and over again. So basically, in my opinion, we need to incorporate multinational research projects into the curriculum, not only at postgraduate level, but at undergraduate level. And we need to instill in our young faculty members the importance of multinational, multidisciplinary research. The third point is that we need to promote more extensive leadership roles of youth and also youth organizations. And I would like to cite in particular UInspire, a UNESCO-related initiative, which now has 12 countries worldwide and maybe 1,000 young scientists working on DR research. And the fourth point is that, we've gone through this COVID business, and we really need to connect disaster health sciences more closely to everything related to water. And within help, we've done quite a lot in that regard, but much more needs to be done. And lastly, the information structures are not sufficient. We need to work on that. So as Professor Koike will show you later, we have some examples about how we are trying to address all of these challenges above in the context of our work with HELP and our alliance of alliances. So what is HELP? Many of you may not have heard about HELP, but it was created in 2007 by Dr. Han Sun-soo, who was the former Prime Minister of Korea and the 56th President of the General Assembly of the UN. And so he chairs HELP, and the co-chairs are two ministers, as you can see below. And the unusual thing about HELP is that half of the members are high-level governmental leaders, either at the ministerial level at their home countries, but also in UN agencies and other international agencies. And the other half of the members are advisors, so the scientists. So it brings together the governmental people with the scientists to help bridge the science policy interface. So of course, the main goal of HELP is to move the issue of water and disasters onto the world stage and help get it into the agenda of national governments and international organizations. Since 2013, every 2 years, we've had special sessions of the UN General Assembly on this topic of water and disasters. The most recent was just a few days ago. And so I show a few pictures. You know, we have Han Sun-soo, the Secretary General of the UN, and the current President of the UN General Assembly. I urge you to look at the video recordings on UN TV of this session, because it was really fantastic. So in this session, there were keynote speeches. I won't read all the people, but I would like to say that in particular, His Majesty the Emperor of Japan gave an amazing keynote presentation. And so I really, really urge you to look at his PowerPoint or the video of him. So as part of this special session, Professor Koike and I organized a science and technology panel before then to feed the science and technology input into the major event. And we were very honored to have our Vice President, Xue Lin, as one of, he gave a keynote speech. And I urge you also to look at that session. And then lastly, in terms of HELP, we have a number of flagship initiatives, one on climate change, led by the Netherlands, another on the important topic of finance and investment, led by Japan, and then this alliance of alliances led by Sichuan University and ICHARM. And you can see below the critical roles we envision for the AOA. We are really anxious to have other people join us. And so now I will turn the floor over to Professor Koike.
Could you please stop the share screen?
Got it.
Okay. Okay, this is Toshio Koike from the ICHARM, International International Center for Water Hazard Risk Management, and Species UNESCO. As Professor Kalonji, my co-chair of the Alliance of Alliances, introduced, we had a very nice science and technology panel session under the framework of the 5th UN Special Thematic Session on Water and Disaster. It is our great honor to have Professor Xue Lin as a keynote speaker in this panel session. The target of that panel is how to enhance sustainability and resilience, especially water-related disaster resilience. So the preamble of the 2030 agenda says in this way: we are determined to take the bold and transformative steps which are urgently needed to shift the world onto a sustainable and resilient path. The concept of the sustainable development has been formed after the substantial discussion on the environment and development in this way, while disaster resilience has been created through the transformation of the idea of the disaster response.
Okay. Professor Kyoki, do you have screen to share? Do you have PPT or you don't have PPT?
I share the PPT.
It's not shown here.
Okay, just a moment.
Right.
Why?
So maybe you click on share screen, go to the screen
Yes.
and click share
Yes.
screen.
Once again.
And all right, it's coming up.
Okay,
yeah, all right,
sorry.
Great, thanks. Yeah.
Sorry for this, but I just introduced the background of this science and technology panel, the titled on enhancing the sustainability and resilience, and also the background of the sustainable development, and also background of the disaster resilience I introduced. I'm sorry, that PowerPoint. And as you know, the number of the water-related disasters, such as flood, cyclone, and drought, has been rising very rapidly due to the climate change by more than 3 times since 1980. The overall economic losses are also increasing at a fast pace. More than 3/4 of the economic losses are accounted for in upper middle or high income countries. However, the economic losses relative to GDP account for higher values in the lower middle and low income countries. Furthermore, more than 80% of the human losses occurred in the lower middle and low income countries. Sustainable development goals. We have 17 goals have been identified in 2015. These goals represent the quality of life component, as you can understand. And this quality of life component is directly supported by water, food, energy nexus component. The natural and artificial environment components are also connected with this quality of life and the water, food, energy nexus component. All the components are deeply related to the social system component. We can understand the 17 goals in this structural way. Water-related disaster intensified by climate change can affect various aspects of society. The impact propagate to water-related, water, food, energy nexus, and the quality of life. Moreover, once society falls into such circumstances, more problems arise in such area, gender, equality, and peace to a great degree. The throughout the COVID-19 pandemic, the world learned that complex, cascading, and systemic risk that are urgently implicit in social, economic, and environmental systems can suddenly emerge and threaten humanity beyond the boundaries in space and time. How should humanity survive such a risk and live with them in a sustainable way? This is the fundamental question. So to discuss this key question, we had 5 distinguished panelists through the network of Alliance of Alliances. One person from the Assistant Director General of the Natural Science of UNESCO, one person, Deputy Secretary General of the World Meteorological Organization, the other person, the Director of the United Nations Disaster Risk Reduction, UNDRR. And we also invited 2 representatives from the countries. The one is from Mexico. She is the Director General of the National Water Commission. As a person from Malaysia in Asia, she's a professor of the university and a project leader of the Southeast Asia Disaster Prevention Research. They introduced their activity and they respond to our key question. So we set up our key direction. Sustainable development and disaster resilience are closely and structurally interlinked. So that's why we need to understand issues related to the resilience and sustainability in a comprehensive manner. We also need to study their causes thoroughly, and we need to conduct planning, implementation, and evaluation for resolution. And we should construct a cyclic structure to create a better future. So the more contribution of science and technology and the more effort of the whole society are essential to enhance sustainability and disaster resilience. This is our agreed key direction. The UNESCO Assistant Director General emphasized to promote the open science. Open science is a key for the bringing the people to action, to take action. The Deputy Secretary General of the World Meteorological Organization emphasized this science must support development of the policy, strategy, and operation. And observation, prediction, research, and warning services should be a public good. So we need to share this chain. And our colleague of the director of the UNDRR emphasized the systemic risk. And what is the tipping point in a society? And we need to address multiple systemic failure to get a better link to sector regulation, planning, enforcement standards, and good practice. So the Director General of the government, the Mexico government Water Commission, emphasized her experiences. So we need internally the coordination among the various sectors related to the water, but the intergovernment, the coordination or teamwork has not been successful. So we need to improve such kind of integrated the activity through the coordination in advance. And the professor of the leader of the disaster management in cooperation with this, in this case, in her case, is she cooperated with Cambridge University. So she emphasized to create a collaborative mechanism to exchange of the academics, researchers, and practitioners at a local level. The capacity building of early career scientists, youth, and young professionals is really important, and action-oriented research partnership and science policy interfacing should be enhanced. So based on these input from our panelists, we summarize and then identify the concrete action. So firstly, we should promote open science policy, which guarantee open access, open data, and open to society. Science needs to be more closely connected to the social needs by promoting equal opportunity for all and strengthening the science policy interface. Secondly, it is crucial to find systemic solutions through interdisciplinary and transdisciplinary collaboration and strengthen the risk communication. In addition to data and knowledge integration by the science community, this is very important, individuals should be able to access the information, especially on experiences in the experiences of local experience in their mother tongue. Thirdly, on-site stakeholders should develop integrated scenario and execute the concrete measures by sharing the understanding of the systemic risk through every dialogue and making maximum use of the global monitoring as a public good, forming a cyclic system of consilience, integration of the knowledge, and discovering the relationship of the cause and effect. And we need to deepen the quantitative understanding. Lastly, but not least, the international society should support all stakeholders in taking concerted action to enhance government teamwork through this tripartite cooperation among the science, policy, and operations. At a different spatial scale and semantic and functional terms. These four actions we identified and we need to take through the discussion of the panel. So how to realize these actions? So I think I would consider how to promote the open science and support the on-site stakeholder to develop integrated scenario and execute concrete measure. From the science point of view, myself, we need some synthesis system in online basis for sustainability and resilience. So we need a function for exploration, collection, archive, and search of the scientific information in mother tongues. And we also need to improve prediction ability and simulation and visualization, and data integration and information fusion, and coordination beyond the different disciplines. Based on these functions, we can develop the resilience in a science community. However, we should identify there is a gap between the science community and the society and the on-site stakeholders. So to fill the gap, it's very important. For that purpose, we need an external function, that is a facilitator, which is not just a master of ceremony, but a catalytic being. So who has this kind of the function? Based on the new viewpoint from the science community and the communication function through the online system, the facilitator can try to fill the gap between the science community and the on-site stakeholder. Then user needs and the local knowledge can be shared with the science community by a facilitator. As a result, the science community can propose a new framework to the society for getting fresh learning with regard to the disaster resilience and sustainability. So we consider this kind of the framework and try to implement this framework in a society. This Wadid Africa, water disaster platform to enhance climate resilience in Africa, we developed this project in cooperation with UNESCO and local alliance. In a Volta River Basin Alliance and Niger River Basin Alliance, totally 11 countries. But just after the launch of this project, COVID-19 spread worldwide and interrupted a majority of the fieldwork. Only through the remote communication and cooperation under COVID-19, we developed a regional flood early warning system on the data integration analysis system, DIAS, in Japan. And we also developed two-tier e-learning programs, training of the expert, TOE, and training of a trainer for fostering the facilitator. Through 4 weekly sessions of the TOE, totally the 197 participants among the 288 passed the evaluation test. From the TOE winners, totally 44 were nominated as a TOT participant. Finally, 30 participants were awarded as a facilitator through the 2 weekly sessions of the TOT. This is an example of the activity of the Alliance of Alliance. In a regional scale, this one is the national and more local scale. In collaboration with the government of the Philippines, we established the platform, which is led by 2 ministries. One is the Department of the Public Works and Highway. The other one is the Department of Science and Technology, by inviting more than 20 national the organization and 3 universities. And we focus on the Davao City in the Mindanao Island, and develop online system for sustainability and resilience, which consists of the flood monitoring and forecasting and climate impact assessment. These systems can provide usable information for decision making, policy making, prior investment, and local practice. To foster the facilitator, we prepared the e-learning system, and we set up the 10 courses, and within 1 month, we provide this e-learning course in collaboration with the local university in Philippines, and also the Japan Meteorological Agency and ICHAN. And the Davao side identify the 4 criteria as the participant in this program. Totally 29 experts were nominated and joined this facilitator training program, and we completed with a very successful result. So this is the one of the example of the national and local scale activity by AOA. I would pass the microphone to Professor Kalonji again.
Thank you, Professor Koike. So I would just like to say that we're very excited to present to this conference today, and we hope that it will not be a one-off event. There can be some follow-up and how to work together in the future. Of course, not only with the conference organizers, our own university, but also with the IHR. And I think you've seen from these examples that we have this huge number of existing organizations, and the challenge is how to make them work together more effectively. And we've tried to illustrate how, with help, we're trying to do that. And we look forward to other interest in new collaborations. Thank you.
Thank you both. This is extremely timely topic, and I guess we'll probably take a few quick questions.
Okay.
Yes.
So I have questions for Professor Koike. Is he still here?
Yes.
So Professor Koike, I'm Chen Xiaotao from IWHR. I'm very happy to meet you in this online symposium. Thank you very much. Share us a lot of information about the international collaboration on disaster reduction. As I know, ICHM just won the chance to hold the 9th International Conference on Flood Risk Management in Tsukuba in 2023. So would you like to say a few words about this conference? Then more people, more Chinese experts were interested to attend.
Thank you very much for giving me this opportunity for advertisement of the ICFM 9 to be held in February 2023 in Tsukuba. It's a great the honor to host the meeting, and we will focus on the topic, main topic, the enhancing water-related disaster resilience and sustainability, and this will be held the Wednesday, Thursday, Friday, but on Tuesday, just before the 3 days meeting, we will have a health symposium at the National Graduate Institute of the Policy Study, GRIPS, in collaboration with, of course, the Professor Gritchen, of course, and the high-level member of the HELP. So we would have a high-level meeting and also the scientific meeting, the totally 4 days. So we are very happy to have many of you to join this opportunity. Thank you.
Thank you. Any other question? Yeah, one more here.
Hi, Professor Toshio. I'm Yang Song from Chongqing Jiaotong University, and I have a question for you. I noticed that you mentioned social eco-development. So I think there is a balance between development and ecosystem. I think we should focus on their shield. Do you think so?
Yes, that is very important. In some cases, the flood control infrastructure for flood control or water-related disaster mitigation affect the negative impact of the environment. But how to manage the disaster risk reduction and environmental conservation and sustainable development. That is the key topic of this framework. We can identify what is a disaster risk. The disaster risk consists of the hazard and vulnerability and exposure and coping capacity. With regard to the vulnerability and exposure are closely related to the development, environment and development. So to realize the sustainable development can contribute to improve the vulnerability and exposure by applying the well-designed urban planning and also the reduce the poverty and improve the education. Then vulnerability could be improved. So we need to consider both simultaneously and comprehensively. That is my proposal.
All right. Given the time.
Thank you for your answer.
Given the time limit, we will move on. Please join me in thanking Professor Kalanji and Koki again for the exciting talk. We will move on to the last talk, which is given by Professor Hubert Johnson from University of Queensland. Professor Johnson did spend quite a few years working on environmental fluid mechanics and hydraulic engineering. And he has published over 1,200 refereed journal papers and 24 books. He has written over 24 books. Any of you who work on air water flow must have read tons of his papers he has authored. Okay, Professor Johnson, the floor is yours.
Thank you, David. Can you hear me and can you see my video?
Not video, we can see you for sure.
Right.
You share your screen.
So let me share the screen then to make sure things are starting properly. And please let me know if you can see properly my PPT now.
Yes, we can see your screen well. All right, you can go
All
ahead.
right. Thank you very much, David. Thank you very much, everyone. Good morning or good afternoon. First of all, I will start with an apology. I cannot be with you physically, and I'm really sorry for this. Physically, I'm located right now in the city of Brisbane, in Eastern Australia, among koalas and wallabies. And I'm not talking just figuratively. This morning, during my morning run in the forest park across my street, I meet with a young wallaby. But let's go back to the topic of this presentation, water disaster. Our society, our communities are facing hydrological extremes with spatial and temporal variability and uncertainty. On one hand, we may be facing very hot temperatures with long drought, multi-year drought, like in part of Africa, Asia, Australia. At the same time, our communities may be facing extreme rainfalls of duration ranging from a few minutes to several months. Intense rainfall, which in turn lead to massive runoff on mega floods. Thus, our species, mankind, is facing a conundrum. In one hand, we cannot survive without drinking water. On the other hand, floodwaters constitute a massive natural hazard. And thus, one of the most efficient means to provide both long-term water reserve, but also flood protection, is through the construction of man-made reservoirs and dams. Dams that need to be equipped with a spillway system, a device aimed to pass safely the floodwater. But strictly speaking, a spillway has two main purposes. First, the safe conveyance or transportation of the floodwater, and secondly, the safe dissipation of the kinetic energy of the floodwater before they rejoin the natural river system further downstream. And here today, I'm going to focus really about energy dissipation. Energy dissipation at a spillway may be achieved at the downstream end using a hydraulic jump steering basin, an impact dissipator, a plunge pool, a flip bucket, but this may be assisted and complemented by using macro roughness down the steep chutes. And today in 2021, the most efficient approach to macro roughness is to use a staircase invert or a stepped invert. And we will be focusing on the step spillway, on the step spillway design today. At prototype scale, and remember that we are looking at real system. The top right picture shows hydraulic jump at the downstream end of a smooth chute. The bottom right photograph shows 10-meter deep plunge pool at the bottom of a smooth chute, while on the far left, you see a smooth chute ending up with a ski jump taking off and impacting further down on a rock foundation. In contrast, a step spillway would have this kind of staircase steep chute with at the downstream end a stealing structure, either a small roller bucket on the left or a hydraulic jump with baffle blocks on the right. And in operation, this is a spillway that you saw on the right photograph. You see here the flow down the steep chute with the hydraulic jump steering basin at the bottom with very turbulent flow. This is a photograph which was taken with a shutter speed roughly about 1 in 1,000 of a second. Step spillways can be found anywhere on the world, worldwide on all continents, except possibly Antarctica, unless we consider the ice cascade at the outer edge of the shelf during the melting period. Through these few photographs, we can see a very broad range of shapes and applications, from small to large structures. Here, a few other examples. And in the next 20 minutes, I will share with you my experience on step spillway hydraulics as stress, hydraulics. I'm a hydraulic engineer. I'm not a structural engineer. I've been working on step spillway hydraulics for close to 30 years, something which started as a pedagogical exercise when I was developing my lecture note for the hydraulic design of small dam and spillways for a master coursework, and become a fairly major research topic with a combination of physical modeling and multi-phase flow analysis. We developed, built, and operated a number of physical models at the University of Queensland, with a few photographs in front of you, with chute slope ranging from 3 degrees to 51 degrees. And behind this fairly large range of longitudinal slope, we also tested a fairly wide range of step geometries, ranging from smooth step, rough step, gabion steps, and so on. So let's go back to the step spillway design. The step spillway design is a fairly ancient design, which has been in use for more than 3,000 years, with a broad diversity in the range of design. Diversity that is linked to a wide range of application, from reoxygenation cascade to sabot mountain protection system and concrete gravity dam. But diversity also in relation to the construction material typologies, from timber crib to conventional concrete, from gabions and rhino mattresses to shotcrete on RCC. Diversity also in terms of the wide range of design discharge, with unit design discharge from less than 0.1 square meter per second to more than 100 square meter per second, over 3 orders of magnitude. And irrespective of the geographical location, of the design application, of the construction material, we are dealing at design on non-design flow condition to some very complicated hydrodynamics, which in turn implies that the engineers need a high level of hydraulic engineering expertise. And this is something that I will emphasize again and again in the slide to come. So, why is step spillway hydraulics so complicated? Why some high level of hydraulic engineering expertise required? Let us look first at a few photographs of step spillway in operation. While they tend to have roughly the same appearance, we can start to see a few differences from one application to the others. We of course can see a lot of white waters, and this would be one of the common features of nearly all step spillway in operation. But we may have also different features, which in turn mean that the flow property down the spillway and at the end of the spillway can be substantially different. For example, if you look at the top right photograph, you see an overflow down the gabion step spillway with a fairly significant amount of seepage flow. And even at large discharge, the seepage play a key role. In fact, we found that energy dissipation down a gabion step spillway is much less than on a smooth concrete step spillway. And then at the bottom, you see some large prototype in operation with fairly significant discharges. This video, and I hope you will be able to see it properly, this video shows the Hinds Dam step spillway in Eastern Australia in operation in 2017. I took this photograph, this video, sorry. The flood was a 1 in 100 year event with a unit discharge of about 27 square meters per second, which is, by the way, much less than the design unit discharge. If I replay the video, have a look at the step height, about 1.5 meters, but fairly large. And at the bottom, we have a hydraulic jam steering basin with a very turbulent flow above the buffer blocks. Some of the key features, but also some of the key challenges associated with step spillway hydraulics start first with a very strong turbulence and intense air entraînement in all prototype operations. In all prototype operations. Very strong turbulence that is directly induced by the staircase inverts, with flow separation at all the step edges, mass and momentum exchange between the cavity recirculation and the mainstream, and the shading of large-scale vortices within the mainstream. And in turn, we observe very high turbulence level in the mainstream flow, with turbulence level anywhere between 20 to 100%, well in excess of what is observed on a smooth chute. For those who wonder about the bottom graph on this slide, there's a vertical distribution of turbulence intensity for the water phase, for the interfacial velocities, and also as well as some sidewall. But this very strong turbulence is conducive of very intense free surface aeration, because the turbulent kinetic energy acting next to the free surface is much greater than the capillary and gravity resistance. If you look at the bottom photographs that are high shutter speed taken on the prototype speedway, shutter speed roughly about 1 in 8,000 of a second, we can see some massive explosion with ejection of air and water as well as engulfment of air. And in turn, further downstream, we observe death at very large air content anywhere between 30 to 60%. This is huge. This is basically meaning that the main map of the flow is a 50-50 mix between air and water, and this does not include the air placed into motion above the water surface. For your curiosity, the graph on the right-hand side shows laboratory measurement of the void fraction distribution, top graph on the death at very large air content on the bottom graph. Second key challenge, very different flow regime with markedly different flow properties. That is, for a given chute, for a given geometry, depending upon the discharge, we observe one or another flow regime. If we take, as an illustration, one of the simplest case, smooth horizontal steps with impervious material, for example, concrete steps, on a prismatic rectangular channel, we may observe three flow regimes: a jet flow or nap flow for small discharge, a transition flow with massive instabilities for a range of intermediate discharge, something that we don't want to design for, and for larger discharge typical of modern concrete gravity dam, a skimming flow, which to some extent is going to be the focus of this talk. The photograph here on this slide show in laboratory the free flow regime, and on the following slide you see the same free regime at full scale in prototype application. But if we are dealing with more complicated application, we may have a larger number of flow regimes to consider. For example, on gabion step chute, we know that we have 4 different flow regimes which may occur. If we are dealing with pooled step, that is a step with a small wall at the downstream end of the steps, we may have more than 6 different flow regimes, all of which being very different one from another. Third challenge, hydraulic modeling. When we talk about hydraulic modeling, many people like Professor David Zhu and myself will think of physical modeling with, for example, on the right, a student doing some measurement in the channel. Indeed, physical modeling is very common, but it is well acknowledged in the literature that step spillway modeling must be conducted in large-size facility with large discharges. That is, with Reynolds number greater than 10 to the 5 to 5 10 to the 5 to minimize scale effect. And the key word here is minimize. We cannot prevent scale effect. We can only minimize this. But already this requirement means that we need to design, build, and operate large facilities that are expensive. We also have some very turbulent flow, as you see on the photograph on the right-hand side, with a lot of white water, which is good to minimize scale effect. But it means that we need to use advanced multi-phase flow instrumentation, which again are expensive. But equally important, we need to have the people, men and women, with the relevant expertise to perform multi-phase flow measurements. And this is not trivial. Let me give you two thoughts. First, let us think of the teaching of hydraulic engineering and civil engineering at university. At undergraduate and at master level, we do not teach multi-phase fluid dynamics. Our young graduates are not prepared for this type of work. Similarly, in my own university, second thought, when I have a new student who is going to start to do some air water flow measurements, I need to educate and train the individual for 3 to 6 months, sometimes more, before I can start to trust the data set of this new student. But equally important, numerical modeling. This is something that is more recent, and when we are dealing with hydraulic structure, we often mean CFD, computational fluid dynamics modeling. And there, I'm going to be blunt with you. Most CFD modeling of step spillway is rubbish, crap, physically meaningless. And here, I'm sharing my opinion as an expert consultant for government agencies and a journal editor. More than 80% of the reports or the journal manuscripts that I review are physically meaningless because there's an absence of validation. And sometimes I wonder whether these modelers think that CFD is like Xbox or PS5. But behind this problem, another issue is a lack of computational resources. Nearly all detailed numerical studies of step spillway, and I stress of step spillways, are conducted at a laboratory size, which in turn means that the results need to be extrapolated at full scale with the same well-documented scaling effect that we know with physical modeling. And I will come back in a few minutes on this. But if we use an expression commonly used on construction sites, and I work on construction sites, so I know, rubbish plus rubbish equal rubbish. So, what can we do? I've shown you a lot of challenges, and I've been sometimes very crude and fairly negative. What can we do about it? How to move forward? Which way to go? In the next few slides, I will share with you 3 main directions, what I call 3 hints. So the first one that I call right now as a present, it's advanced physical modeling, with 2 to 3 universities worldwide having that capability to the best of my knowledge. That is using a combination of large size facilities with advanced instrumentation and equally important complementary metrologies, whereby we can systematically double check and triple check our data. For example, using dual tip phase detection probe, like you see on the bottom right, with optical flow technique, like you see on the bottom right, sometimes combined with total pressure probe, and so on. But the key word here is using complementary metrology to systematically check and triple check our work. The near future is hybrid modeling, in my opinion. Hybrid modeling in hydraulic engineering is an expression which means a combined or complementary usage of physical and numerical modeling. And in step spillway, we mean physical modeling and CFD modeling. And there, I want to praise the work of Professor Fabien Bombardelli and his research group. They have done some fascinating work on the non-aerated flow region with a few examples on this slide. But at the same time, Professor Bombardelli is the first to acknowledge the limitation of this approach with air-water flow. There's currently not enough computational resources, even using supercomputer, to be able to model the air entrapment and ejection. But equally important, the cost. To conduct hybrid modeling, you need on one hand a team of physical modelers with large size facility. On the other side, you need a team of CFD experts with supercomputer access. And you need a third group of people. You need some people who are expert in the validation process, people who are familiar with both the CFD and the physical modeling. And this is not trivial. I will share with you what I consider as another form of the near future, hybrid modeling Mark II. And I hope the photograph will give you a hint. That is combining field measurement with physical measurement in laboratory under controlled flow condition. For example, on the far left, you have a prototype steps operating with a dimensionless discharge DCO value equal 1.6. Dimensionless discharge is equivalent to a Freud number. The middle photograph shows for the same dimensionless discharge a laboratory in operation with a Reynolds number of 10 to the 6th. So it's already a fairly large physical model. And in laboratory, we can use a series of instrumentation and obtain, like you see on the far right, the contour map of the surface turbulence. And then conceptually, one may think of the framework where on the left, you have field observation with contour map of the surface velocity for that particular prototype pseudo in operation. On the far right, you have the laboratory observation with complementary instrumentation, which can give you, for example, the surface velocity map. But then one will ask, how good are the comparisons between the two? The bottom graph in the middle shows a comparison in dimensionless form of the surface velocity as a function of the elevation down the spillway. The dashed red line is the ideal fluid flow theory, the Bernoulli principle if you want. The cross are laboratory observation using Prandtl Peter tube, and the green and blue are field observation using an optical technique. It's not perfect, but that's already a bloody good agreement if you want my opinion. Now, while I've shared with you 3 hints, we need to stress also the total cost associated with all these different approaches. Total costs, which include not only the yuan, the dollar, the euro, but also the human resources, the men and women who will undertake the work, but also the time required to conduct this type of studies. Professor Bombardelli, with hybrid modeling Mark I, has worked nearly 15 years to develop his current techniques. I've worked more than 20 years in physical modeling on step-way, and in terms of hybrid modeling Mark II, that's nearly 12 years that I've tried to develop this approach. One should not understate the required investments. But I think we need to go back a little bit to the beginning of this talk. Why does it matter? Why is it important to predict accurately the hydraulic characteristic of a step spillway? It does matter because we need to estimate accurately the energy dissipation down the spillway system, down the step spillway, and in turn, to design efficiently the downstream steering structure. Any error, uncertainty, bias may in turn have an impact on the prediction of the rate of energy dissipation and potentially impact on the dam safety. We should not underestimate the rate of energy dissipation down the spillway. This graph shows the spillway outflow, the discharge over the step spillway of the Paradise Dam between 2010 and 2013, a 3-year period during which the step spillway experienced 4 flood events. And I myself witnessed 2 of this, and I'm sharing here a photograph of that I witnessed. During that period, the peak outflow was 18,000 cubic meters per second, which is less than 20% of the design research, and yet the rate of energy dissipation was 7.5 million of kilowatt. That is a rate of energy dissipation which is greater than the electrical output of 8 nuclear power reactors. 8 nuclear power reactors. So if we design a spillway and we underestimate the energy dissipation down the step spillway, we may end up like here, to a damage to the spillway. In this particular structure, the outflow through the spillway was greater than the design capacity, and the spillway was fairly heavily damaged and had to be repaired on the following years. In some cases, the failure of the step spillway can induce a damage to the dam with potential impact on the integrity of the structure, as we see on the top, a dam in UK, and on the bottom left, the complete failure of the dam because of the inadequacy of the spillway system. Clearly, it is critical for the dam safety to estimate accurately the rate of energy dissipation. Let me illustrate two small examples. First, if one performs some study, let's say physically, in a small size facility, neglecting air entrainment, it is well understood and acknowledged in the literature that we will often overestimate the water depth on the spillway by 100 to 150%, which means that in turn, we would underestimate the rate of energy dissipation by more than 300%, which is simply not acceptable. Even if we are doing more advanced measurement, but for various reasons we have some errors, let's say about 30% on the water depth, error which may come because the experimentalist is not well trained, or the CFD modeler is not validating properly the work, or there is some instrumentation error. We could easily have some error on the rate of energy dissipation well in excess of 100%. Again, not acceptable. But equally important, and this is, I believe, directly relevant to some of the previous talk today, we need to put this in a broader context. We need to think carefully of a massive spillway capacity reevaluation, worldwide, for older products as well as new projects. Let me illustrate two examples closer to the city of Brisbane. The Yate Dam in New Caledonia, designed in the 50s to pass 5,500 cubic meters per second, on which discharge in 1992 8,000 cubic meters per second on the current spillway has been designed for 12,000 cubic meters per second, 3 times the original spillway capacity. In Brisbane, close to us, our water supply comes from a reservoir called the Wivenhoe Reservoir or Wivenhoe Dam. The Wivenhoe Dam was designed and built in the 1980s with a spillway capacity of 12,000 cubic meters per second. 20 years later, the spillway capacity was doubled to 27,000 cubic meters per second. And right now, we are talking to enlarge the spillway capacity to 50,000 cubic meters per second, doubling the spillway capacity every 20 years. Clearly, this has major implications on the operation of the spillway, but also on the rate of energy dissipation and potentially dam safety. So as I reach the end of this talk, a few slides of conclusion. I hope through this talk I've shown you that there is a broad diversity in step spillway design, application, construction material, flow condition. And altogether, there is not a unique, simple design method. One of the key features is that whether we're dealing with design or non-design flow condition, we have a complicated hydrodynamics above the step spillway with a highly turbulent flow associated with intense aeration, which means that our design engineer or hydraulic design engineer need to have a solid technical expertise. On one hand, in terms of the positive, I would say for the past 2 decades, we have developed some basic methodology for reasonably sound physical measurements. We also start to have a solid understanding of the operation of a step spillway for simple geometry. On the negatives, however, I believe our CFD expectations are far too high, and we cannot currently trust really CFD. But equally important, we are missing field observation. Let us remember the reference are field measurements that are currently inexistent. Equally important, we are missing validation data sets. That is, we are missing physical data sets that could be used to validate numerical modeling. And I'm talking here about data sets that might not be published in a journal, but will be directly relevant to numerical modelers. So as a final slide, as a final advice for professional engineers, let us remember that steps release are not so simple, and that in 2021, we need still to rely upon physical modeling. For young researchers, my keywords are multi-phase flow, multi-phase flow, multi-phase flow. Thank you very much.
Chanson for this exciting talk. We have time for a few questions. I'm sure we are not hungry yet, right? Or maybe I can ask a question, because for the air-water flow, you talk about scale. Okay, yeah, sure, go ahead.
Thank you for your talk. I think this is very interesting. I have a question for the scale effect. So you mentioned that the scale effect is not negligible and cannot be avoided in the modeling. You mentioned geometric similarity and Froude similarity. So in physics settings, geometric similarity usually cannot be realistically implemented. So most applications will rely on Froude similarity or similar items. This will cause distortion. You mentioned about hybrid modeling as a potential powerful techniques in the future, but have you ever considered about new technology in scaling? So to scale in a more physical sense. Thank you.
Look, thank you for the question. Scale effect is indeed very challenging. And I'm not sure necessarily to follow your question, but I will try to summarize a little bit the current state of the art. A step spillover flow is a free surface flow for which gravity effects are always important. And naturally, we will typically use a Froude scaling and distorted Froude scaling. However, we also will use usually the same fluids, air and water, both in laboratory and at full scale, meaning that the Morton number will be an invariant, will be a constant. But in turn, when we use a smaller model, that is smaller than prototype, the Reynolds number will typically be underestimated. There is no way that with a Froude and Morton similitude, we can have the same Reynolds number in a laboratory. Some of the option or some of the possibility would be, of course, to use different fluids. Everyone is very welcome to try. But I think the current consensus among the community is that air and water are the cheapest fluid available in a hydraulic laboratory. But this is certainly one direction to consider, using with different surface tension and viscosity and possibly density. In relation to scaling, where I believe there are some opportunities to try to combine physical modeling with other forms of modeling, which may not be affected by scale effect. For example, I mentioned hybrid modeling Mark I with CFD modeling. We currently are not able to do some detailed CFD modeling at full scale with the level of detail that we would expect. But maybe in a few years' time, we may be able to achieve this, and the hybrid modeling Mark I may provide us some relevant details and validate or invalidate some physical modeling results. I think hybrid modeling Mark II is also quite an opportunity because field measurement will constitute the reference. If we're able to validate some information from a physical model based upon a comparison with field observation, we may start to get a greater level of confidence. But we all know that field measurements are extremely difficult, not to mention dangerous. I think right now, in my opinion, and this is a personal opinion, there is an absolute need for doing full-scale prototype measurement in the step suite, not necessarily a very large step suite operating at Reynolds number 10 to the 8, 10 to the 9, but maybe a small step suite operating at Reynolds number around 10 to the 6 to 10 to the 7.
Okay, thank you. Any other questions?
Professor Johnson. Well, you know, for a practicing engineer, sometimes simple empirical relation may be helpful for them to choosing or to compare different ways of energy dissipation. So, do you think it's possible to have a simple expression, a simple empirical formula for the energy dissipation rate in terms of, for example, the geometry of the steps and probably also the flow conditions? And another thing is that do you think it's possible to have a simple critical condition for estimating? I mean, when the air entrainment occurs.
Thank you. Look, I think your question is timely because design application is really one of the key focus of current research. And in fact, the research on stepway has been driven for the past 30 years by the industry, by the engineering needs. To come back to your question in relation to a simple formula, I think the first point that I want to make is that the hydraulics of a step chute is much more complicated than the hydraulics of a smooth chute. And thus, I believe that the design of a step chute is not for a junior engineer using a handbook or a nomograph or a simple formula. It has to be undertaken by someone with experience in hydraulic engineering. When we are dealing with simple geometry, for example, smooth horizontal steps, impervious material with prismatic, for example, rectangular prismatic cross-section, the flow is quasi-two-dimensional and there is already a number of fairly robust results which could be applied for practical applications. But as soon as we move away from this very simplistic geometry, the flow becomes extremely complicated and there is not really simple design formula. Even for a design office, and I'm working as a consultant to assist some industries, we need to rely heavily upon physical modeling and upon numerical modeling. And often we use hybrid modeling where we combine the two together. So in first part of your question, simple formula, it's not that simple. In relation to air entrainment, I think we can provide some guidelines, and I think there are already some guidelines upon the prediction of when air entrainment will take place. That is already very useful for professional engineers. But once air entrainment takes place, there is currently no magic simple formula, unfortunately.
Okay, I guess we'll close this morning session. So thanks everybody, and I know it's kind of late. Professor Peter Gerwin's still there. I guess it's already past midnight now. Okay, thanks for sticking around. Again, join me in thanking all the speakers of this morning session, and I find the talk all are wonderful, and I'm sure we'll have a lot of discussion we can follow up. And hopefully we can have you guys coming here, join this meeting next time. Again, thanks everybody.
Thank you.
I guess this is lunchtime. The afternoon meeting starts at 2 o'clock. Okay, thank you. Okay.
参见有。